This is the first time in the entire history of integrated circuits. We're at the very heart of our computers, in the processor chip. Now, it's not across the entire processor, but it's in a vital memory part of the processor. So are you intrigued how these bits work? And are you interested how they could impact today's information technology and the technology of future? Yep. Thank you. So I am Tomáš Jungwirth. I work at the Institute of Physics of the Czech Academy of Sciences, also at Nottingham at the university. And our Prague group has a footprint in this technology. So as a warm-up, in this first animation, let me take you to the end of the Second World War. Let me bring you inside the computer that was running the Manhattan Project. And what we see is how the bit worked at that time. The bit was a magnetic relay. Magnetic relay discovered in the mid of the 19th century by a guy named Morse. Guys, you remember Morse code? Telegraph, that's the guy. And this was the technology of the bit. There is an electromagnetic coil that is generating a magnetic field, and this magnetic field is lifting the magnetic arm. And this disconnects the circuit. There is no current flowing, there is no bulb shining, and we have logic 0. On the other animation, the magnetic coil is releasing the arm, and the circuit closes, and this represents the logic 1. At the very same time, we're talking about the mid-1940s, there was a discovery of the so-called transistor, or shortly transistor effect. It was a truly remarkable discovery because simultaneously it removed the two fundamental problems or limitations of the old magnetic relay bit. First, it removed the magnetic field, and we do not want to have magnetic field in our circuit because they could interfere with remote bits on the circuit. And second, we do not want to have any moving parts. Transistor make the trick how to remove these two limitations. So let's take a look at the transistor. The transistor has a conducting channel. In this channel, we have electrons, the elementary particles that are carrying the electrical current. Now, we have a central gate electrode, and when this central gate electrode is charged, it removes the electrons from the channel. The current stops flowing, and we have the logic 0. Once the central electrode is not charged, the electrons coming back to the channel, they can carry the electrical current, the circuit is closed, and we have logic 1. The discovery of semiconductors and the transistor was one of the first victories of modern quantum physics. And it led to one of the first Nobel Prizes for quantum physics to these 3 gentlemen, Barden, Breton, and Shockley. The invention of the transistor itself was truly remarkable because it started and it completely dominated the information technologies until today. Why is it so? Because transistors have the property that they could be miniaturized. And what happened between then and today is that the size of the transistor was reduced billion times. The problem, though, is that now transistors are running out of breath. With this miniaturization, it's becoming excessively expensive to fabricate those transistors. And even for some applications like memories on your chips, on your processor chips, they stop working. So that brings me to the new Spintronic technology for bits. Spintronic bits are magnetic. So what it means is that now magnets are having their little payback against semiconductors. Magnets are coming back to the central stage. But they are coming back in a completely new reincarnation. What we see here is the spintronic bit. It comprises 2 magnetic electrodes, but they are super tiny. They are made of just a few atomic planes, and the 2 electrodes are separated by a very thin spacer, again made of just a few atomic planes. And the new quantum physics trick that enables this technology is that now, and again, this is the first time, we're not only using the property of electron, which is its charge, to make electronic devices. We're using the second property of an electron, which we call in physics spin. But what it is that it gives the electron the property of being a microscopic magnet itself with its magnetic poles. Now, in a material like iron, which we perceive as a big magnet, what happens is that all electrons in our iron crystal, they decided to align their magnetic poles in parallel. And the combined effect of these teeny tiny magnets of electrons is what we perceive at the outside as a magnet. So what happens in our bit? These electrons, with their microscopic magnets, are trying to move from one magnetic electrode to the other. When we are in this scenario of logic 1, when the 2 magnetic electrodes have their poles in parallel, electrons with their small microscopic moments inside, with the small microscopic magnets inside, when they're trying to hop from one electrode to the other, they see that the environment is the same, the magnet is the same, and they can happily flow through the device. The circuit is closed, and we have the logic 1. Another discovery, now a late 20th century, and another Nobel Prize. The phenomenon we call the magnetoresistor effect. Why is it so fundamentally important and interesting? Because now we have a magnetic bit which has no magnetic fields needed to operate it. Everything is electronic. And there are no moving parts. It's even better than the transistor in a sense that we do not have to remove the electrons, the light, tiny electron particles from the channel. They can still remain there. The only thing that we are controlling for the operation is their internal magnet. We are flipping the poles of the internal magnet. The question now is, what about Prague and all this technology? So now I'll bring you to the beginning of this century. And in Prague, we discovered a phenomenon which is called spin Hall effect. And this phenomenon is now recognized by all major developers and manufacturers of these new spintronic bits as the most efficient way how to write information, how to switch the magnetic electrodes electronically by electrons with their spins in this bit. It's a quantum mechanical trick. All what we use in this technology are, in the end, quantum physics tricks. There is one more trick that we came up with very recently. I told you that we do not need magnetic fields anymore to operate these spintronic bits. But I also told you that the 2 electrodes were made of magnets. So the magnetic fields are still there, and it is the thing of these magnetic fields that's going to limit the density of these memories, but also their speed and their energy efficiency in the end. So the question we were asking is, could we find magnets perform exactly the same electronic functionality for reading and writing as we do now in these modern spintronic bits? but in magnets that do not have any magnetic poles, that generate zero magnetic field that could disturb the neighboring bits. And we have came up with a whole new family of magnets that have exactly this property. I hope that I did intrigue you with physics and what physics can do for information technology, but I guess you might be also wondering, so what? I mean, you've been talking about these elementary particles of information technology, these individual bits, how they work, but this is infinitely far from how we perceive information technologies in our daily life. So on this, let me make one concluding comment. The timing for these spintronic bits was right, not just because semiconductor bits, at least in some parts of the processor chip, are running out of breath. The timing is also right because the entire landscape of information technology is completely changing today. And what happens on the hardware level is that the pressure is actually shifting towards the memory part of the processor chip because we need to process huge amounts of data, and we need to have memories which will have on the chip huge capacity, be fast as the computation unit, and simultaneously energy efficient. And remarkably, Spintronics seems to tick all these 3 boxes. Thanks a lot for listening.